All right, in this podcast, we're going to talk about the concept of half-life. All right, you may have heard of half-life before in terms of nuclear decay, radioactive decay, where a nucleus is splitting up and it's letting off these radioactive particles as it's doing so. So that and what we're going to talk about now, they operate the same way mathematically, even though it's actually technically a different thing chemically. All right, so basically, in terms of kinetics, half-life is the amount of time that it takes for 1/2 of your sample to turn into product. So, in terms of like radioactive decay, it would be the amount of time it takes for half of your sample to decay, to actually let off radiation and change, right? Okay, so like on this graph, we can see that we started with 150. So half of 150 is 75, right? So this right here, whatever that lines up with, okay, that's our half-life. That's the time it takes for half the sample to decay. And then again, so 75 cut in half is 37.5. So after that same amount of time, you will again have lost half your sample. Everything has a half-life, 0, first, second order, but you are only required to know how to do first order half-life, okay? So that makes your life so much easier. So half-life symbol is this T1/2 thing. Okay, that's the symbol for half-life. And the equation, first order equation, is the natural log of 2 over K. So our half-life is equal to the natural log of 2 over K. Okay, so here we go. We've got an example problem. You see that it says it is a first order and tells us the half-life is 4 minutes once the value of K. All right, so we know that the relationship between half-life and K is that, right? So 4 equals natural log of 2 over my K. So if I rearrange that algebraically, okay, so natural log of 2 divided by 4 is my K. So K is equal to 0.173. And then again, for our units, we would do 1 over overall order minus 1, right? So 1 minus 1. So molarity would go away. So basically it's 1 over minutes. Okay, so the second part of the question is giving us, is saying if our initial concentration is 3.6 molar, what's our concentration after 15 minutes? Okay, so what you're going to have to do here is the only thing that you have that relates initial concentration, time, concentration, all that stuff is going to be your integrated rate law. So we know this is first order. So we know the integrated rate law is the natural log of A is equal to negative KT plus the natural log of AO. Okay, so we're going to start looking at stuff to plug in. All right, so A sub O is our initial concentration, so that's definitely going to be over here. And we just found our K just a second ago, and we're given our T, which is 15 minutes. So we're going to multiply those two things. All right, and our 0.173 negative. All right, and then we're going to set that equal to what we're trying to find, which is our concentration after so much time has passed. All right, so now it's just an algebra game. So let's get this worked out real quick. Okay, so we got our 1.281 here. And then over here, our K and our T, we got negative 2.595. All right, so if we go ahead and combine that right there, let's see. Let me get my handy dandy calculator out here. Okay, so I got negative 1.314. Now, that, of course, is equal to our x, which is actually the natural log of a, right? Okay, so we were asked not for the natural log of a, because that's what we found so far. We were asked for the actual concentration, so we actually want a. So, how do you get natural log and a apart? Hopefully you said that we need to incorporate e here. So if we raise everything to the e, then that will cancel out our natural log over here, and so we'll end up with our concentration after 15 minutes being equal to 0.269. And remember, that is molar.